Good morning, everybody. I'm Sebastien LeDuc from Kalray, and in this second part of my keynote, I will go through 3 use cases where using DPUs makes a big difference. So the first use case is basically the main use case for which NVMe over Fabric was invented, namely disaggregating local SSDs. So the idea is pretty simple. On the left, you have servers with direct-attached SSDs, and the idea is to disaggregate the SSDs by putting them in a NVMe over Fabric all-flash array. And so basically, the local SSDs now become a shared pool of storage that is visible to all servers thanks to the NVMe over Fabric protocol. So this has a number of advantages. So the first one is that servers can now be composed on the fly with just the storage requested, whereas on the left, you basically had hard-coded configuration with a number of direct attached SSD in each server. So this, of course, results in better resource utilization and then, of course, has a decrease in costs. The second advantage is that thanks to this new architecture, since the disaggregated SSDs are visible as a shared pool of storage, it's now much easier to move workloads from one server to another one, because you just have to reattach to their volumes after moving them. And another big advantage of this approach is that you can now scale storage and compute independently, again, allowing to reduce the costs. So, of course, shared storage is not new, but thanks to NVMe over Fabric, it's the first time we can have both shared storage with performance close to that of direct attached SSDs. So there are a number of ways to implement NVMe over Fabric all-flash arrays, and I will try to compare those different ways of doing along 2 KPIs. So the first KPI is on the x-axis, IOPS per dollar. So basically, this is a very good indication of the TCO optimization you can get from switching to one solution. And the second KPI that is of interest is IOPS per watt, because power consumption is becoming really an issue in data centers. So we think this KPI will become more and more important in the future. So let's look at the first solution that I call storage vendor solution. So basically, all major storage vendors have some NVMe-oF all-flash array in their catalog today. Those solutions are based on x86 platforms. They are very feature-rich, but since they use some software stack that has not been designed for NVMe parallelism, they are not able to fully exploit the performances that is available thanks to NVMe disks. And the result is that the performances are not as good as what we would like. They are also pretty costly. This is why, in terms of IOPS per dollar, they are not very good. Then another category, still based on the x86 platform, is basically what I call x86-based all-flash arrays, on which you put a software stack like SPDK that has been designed from the ground up to exploit the parallelism of NVMe disks. In this case, you end up with a solution that is an order of magnitude better than the one of storage vendors. But in terms of feature, it's very difficult to put all the storage features while still keeping the performances. The more you add data services, the more the performances will collapse, basically. because the x86 is a general purpose processor, and you don't have the hardware dedicated tightly coupled accelerators that DPUs have that allow them to cope with the additional data services. And of course, the third solution is to build a NVMe-oF all-flash array using DPU cards instead of using a x86. So basically, in this case, since the DPU has hardware accelerators to accelerate data services, it's able to cope with running more data services without decreasing the overall performances. And we see that today a DPU is the best solution when you look at IOPS per dollar, so in terms of cost, versus the two others, or even better in terms of IOPS per watt, because DPUs have a much lower power consumption than x86 based platforms. So in terms of data services, let's go a little bit more into the details of all the data services that are needed to make a storage node, let's say an NVMe-oF storage node. So there are some basic services like TCP termination for NVMe-oF TCP, which takes quite a lot of software processing. Logical volumes, scene provisioning, and snapshots are, of course, basic services that are needed on any storage appliance. And then we have some other data services that are much more processing hungry, like data reduction, data availability algorithms, or data security. So here, the DPU is able to cope with all those data processing services at line rate much better than the x86 because it features some dedicated hardware accelerators like compression acceleration, erasure coding acceleration, or crypto acceleration. And thanks to those accelerators, the DPU is really able to sustain the required performances. So this is why we believe the best solution to implement an NVMe over Fabric all-flash array is by relying on DPU cards. Let's now switch to use case number 2, which I call storage adapter for SSD disaggregation. Basically, use case number 2 starts from where we left in use case number 1. So on the left, we have our situation where we have disaggregated SSDs by using a NVMe over Fabric all-flash array. The all-flash array usage brought quite some advantages, but there are still some issues. The first problem is that you need an operating system on the server that has NVMe over Fabric support, of course, which is not the case of all operating systems supported today. Another issue is that it's not possible today to boot from SSDs exposed via NVMe over Fabric, which means that you will need another medium to boot from, be it another shared storage like iSCSI or local SSDs, just to boot. There is still room some improvement. So this is where the storage adapter comes into action. So the idea is to put a DPU card with a storage adapter software on it in each of the server. And I will explain a little bit more what this storage adapter will do. So the idea is that the DPU in the storage adapter will present itself as local NVMe disks to the host server, and it will be basically the storage adapter that will manage the NVMe to NVMe over Fabric translation. So that's why we call it an adapter. The advantages of this solution is that you no longer have any requirement on the operating system because basically now the server only sees NVMe, and NVMe is supported by all current operating systems. It also means that you can really exploit this mechanism to do bare metal server virtualization, basically. The second good property of using a storage adapter is that now that the server only sees NVMe, it can boot from this NVMe, and it will be the storage adapter that will do the translation to NVMe over Fabric. So at the end, you are now able to boot from NVMe over Fabric disks. And all that is fully transparent to the bare metal server. If we now focus on the NVMe to NVMe over Fabric translation, the translation can be configured by some orchestration software that will interact directly with the DPU through the network, so either inbound or out of band. So you don't need any orchestration software on the bare metal server, and it also means that you can move workloads from one bare metal server to another one, which is pretty nice. So really, as you can see, thanks to this storage adapter in servers, we enable bare metal storage virtualizations by using DPUs. In terms of data services, this storage adapter is bringing a lot of opportunity for system optimizations. In terms of basic services, the DPU will have to handle all the bare metal storage virtualization. So basically, it will have to provide some APIs to the orchestration software so that the storage virtualization can be configured. The storage adapter, so the DPU, must also, of course, implement the NVMe emulation in order to be able to present itself as a NVMe local drive. It also has to support NVMe initiator functionality in order to translate from NVMe to NVMe over Fabric, which by the way, implies that the DPU is running a networking stack. And of course, there are some QoS considerations because you may want to have QoS settings different and configured by the orchestration software. So as you can see, thanks to a DPU, we enable bare metal storage virtualization, and it's fully software defined. Other opportunities for running data services on the storage adapter. So we can, for example, have data reduction algorithms running on initiator side, which has some benefits because it results in lower network bandwidths. And in terms of data availability, now that we have a DPU on initiator side, it allows us to have much better data availability schemes like distributed erasure coding, which enable better reliability while improving storage efficiency. And in this case, again, the mapping of volumes is fully software defined by software running in the DPU and configured by the orchestration software. Similarly, you can have data security services that will run in the DPU. So you can, for example, have encryption in motion that is transparent to the host server that still sees only NVMe drives without knowing that behind the scene there is some NVMe over Fabric translation going on, and that this NVMe over Fabric is encrypted, connection is encrypted. Again, the security configuration in that case is fully software defined and can be controlled by orchestration software. So as you can see, using a storage adapter in each of the server brings a lot of new possibilities, and especially for bare metal storage virtualization. Let's now switch to the third use case I want to talk about today. So the third use case is called storage adapter for hyper-converged infrastructure. Similar to use case number 2, but still a bit different. On the left, if you take a standard hyper-converged infrastructure, you have identical servers, each with both some compute and some storage, so some local disk in each server. The idea is to put some storage adapter in each of those hyper-converged servers and use those storage adapters to provide a global data store repository to the full HCI cluster. The idea, again, is that the storage adapters will connect to each other, and in order to provide a distributed pool of SSDs that become visible to all the storage cluster. So I will go a little bit more into the details in the next slide. In this use case, the idea is that the DPU takes ownership of the local drives in the HCI server. This is using the PCIe peer-to-peer technology. You can have the DPU that will read and write to the local SSDs. So it can really take ownership of the local drives that are no longer under the control of the host server. Then the DPU, similar to use case number 2, presents itself as local NVMe disk to the host server, and the DPUs that are in each of the servers kind of connect to each other and provide a global data store made of all the distributed local drives of the cluster. And this becomes a global data store exposed to the host servers. So in this case, each DPU will act as both a storage target and a storage initiator. And storage is fully virtualized without needing an hypervisor. And of course, this virtualization is fully software defined by software running in the DPU that is configured again by orchestration software. You also have the opportunity to use NVMe-over Fabric all-flash array in addition to using storage adapters, which enables to increase the size of the global repository just by adding NVMe-over Fabric storage nodes in your infrastructure. And this is fully transparent to the servers. They just see additional storage that can be used. And in terms of data services, so this is quite similar to use case number 2. We end up with the DPU that has to support bare metal storage virtualization software. Again, it needs to implement NVMe emulation to present itself as local disk to the servers. It has to implement NVMe-oF target and initiator in this case, because the server, when writing to a volume, may write either to a local drive behind the scene or to a remote drive. So similarly to use case number 2, in the DPU must run some networking stack and some QoS features. And again, all that is fully software defined with software running on the DPU and orchestration software that can configure it. Similarly to use case number 2, we can do data reduction and data availability algorithms or data services that are, again, fully software defined. And you can now, for example, have distributed erasure coding inside your HCI infrastructure without decreasing the performances, because as you may know, in HCI solutions, HCI software solutions, erasure coding is usually not enabled by default because the performances decrease quite a lot when you enable it. Thanks to a storage adapter, you can now offload completely this distributed erasure coding, and you can now enable it all the time. Another good property of using storage adapters is that it enables to use HCI infrastructure for bare metal workloads or bare metal use cases, whereas while still keeping the flexibility of storage virtualization. So this is really something new, and that can be only achieved thanks to a storage adapter based on a DPU. Okay, let's now switch to the conclusion. The NVMe SSDs and NVMe-over Fabric will disrupt the storage markets. That's what we are already seeing on the market today. I mean, the NVMe SSDs are adopted very quickly, and NVMe-over Fabric is following. Today, we really see that software-defined storage based on virtualization will become a bottleneck to leverage the full potential of NVMe-over Fabric. And we believe that DPUs are the solution, and this is what will allow to unlock the full potential of NVMe over Fabric while keeping the flexibility of software-defined storage. Thanks a lot for your attention. Goodbye.